The goal for process data object communication is that we have multiple object dictionary entries that can be copied into one CAN message. So they are mapped into one CAN message and there's no overhead. So it's really data only. We use the maximum number of bytes available in a CAN message for the data transfer. However, if the number of data bytes transmitted are shorter, then also the CAN or CANFD message is shortened. The basic idea behind PDO mapping is that we can take any object dictionary entry, for example here 6001, an 8-bit digital input, and place it into a PDO which later translates to a CAN message. And then we pick the next one, another unsigned 8-bit digital input, but we can combine it really with any other mappable object dictionary entries. So here for this example, take another 2 analog input values and also place them into the PDO. So here we have a total of 6 bytes, 4 entries mapped that go into one CAN message. In the following section, we examine which object dictionary entries configure the PDO mapping. So how do we determine which object dictionary entries go where into a PDO? The PDO mapping parameters are structured in a similar way as the PDO communication parameters. So we have up to 512 TPDO parameters and up to 512 receive PDO parameters. Simple I/O modules or sensors will typically only use a limited number of PDOs, 1, 2, or maximum up to 4. The control units and managers, masters, they typically require more PDOs because they need to communicate to every other device on the network. So that's why a huge number of PDOs can be configured for a single device to accommodate these systems. At each index, we have an array of 32-bit mapping entries, one for each object that is mapped to this PDO. A single 32-bit mapping entry is similar to a pointer in a programming language because it points to the object in the object dictionary that we want to place in the PDO. So the 32-bit value contains the 16-bit index and 8-bit subindex of the element of the object that we want to copy to the PDO. And it also contains the lengths of the data in bits. Please note that for compatibility reasons, you should only use lengths that are a multiple of 8. Some implementations provide bit-by-bit mapping. However, not everyone does. So if you want to stay compatible, please use a multiple of 8. At each index, we have an array, a list of entries, of mapping entries, and they determine the contents of the PDO. So whatever the first entry in the list, in this case 6001, so index 6001, 08, so 8-bit, 1 byte is mapped as first into the PDO. Second, we have 6002, so here the second digital input is mapped into the PDO. And then we have 640101 and 640102, 2 analog input values mapped into the PDO. So down here at the bottom, we have the final contents of the PDO as it will be transmitted. In the following section, we'll have a look at both transmit and PDO mapping. So what kind of mapping do we need to have in place for both a transmitter and receiver to ensure that data goes from the object dictionary entry of one node to the object dictionary entry of another node? For this first example, let's assume we have 2 CANopen nodes with manufacturer-specific entries, an array at 2000 with 4 subindexes, and we'll pick 2 of these elements, put them into a transmit PDO, then the data gets transmitted. And let's assume the receiving side has the RPDO1 configured to receive this data, and we have here an identical mapping so that the data B and D gets into the same location as from the transmitting node. However, there will be situations where the object dictionary entries do not have the same numbering on the transmitter and the receiver side because simply the object dictionary entries will be different. So depending on application and requirements, it could be that what we are mapping here on the transmit side into transmit PDO2 then gets transmitted, and on the receiving side is sorted into completely different object dictionary entries, resulting that here, for example, value C comes from 2000 subindex 3, but in the destination node goes into 3000 subindex 0. That example shows us that really from any object dictionary entry you can transfer data to almost any object dictionary entry as long as it's the same size. The reason why this is used quite a lot is that if you use several same CANopen nodes as a transmitter, so maybe you have 5, 6, 7 sensors that all have the same object dictionary entry layout for their input data, and all this data needs to be merged into a single destination node, then of course in the destination node we need to have different entries for the data coming from different nodes. Otherwise they would overwrite each other. That is illustrated here by the last example. So the two transmitting nodes on the left both have an index 2000 subindex 2. The top one is an X with data, the lower one B, but on the receiving side, so that they don't overwrite each other, we need to find two different object dictionary entries on the receiving side to place the data in. Let's now have a look at how a tool like the CANopen Architect, an EDS editor, handles these entries. I have here a CIA 401 device that is a generic CANopen I/O digital and analog I/O. If I check the standardized device profile, I see we have reads, digital lines, input and outputs, and we have analog inputs and outputs. Now, if I go to the communication profile, then we also have the PDO mapping parameters down here. So let's look at the transmit. So the transmit are here these 32-bit values we saw earlier. So index, subindex, and length all in one value. And down here we also have analog values. Well, in tools like these, it's easier to set these up by going into the PDO section. And here we have, just a second, make this a bit wider. Here we can see all PDOs in a more convenient setup. So here are all the communication parameters, and here at the end are also the mapping parameters. And we see the number of elements mapped, and if I double click on it, a window pops up showing us the elements mapped. And if we want to make changes, we can just click on here and do point and click remove to. So let's say we would like to combine it as in our example. So here's two digital inputs. And now we add another analog input. So that is standardized device profile, read, and here we go. And going back to the original settings here at 1A00, we can see that there's now 3 entries. And so here is the digital one, the digital 2, and here we have the analog value. Reviewing the different CANopen and CANopen FD communication methods, we can say that the difference between a CANopen PDO and a CANopen FD PDO are primarily the size. So a CANopen FD variant of a PDO can have up to 64 bytes, whereas a CANopen PDO is limited to 8 bytes. Other than that, PDOs are always multicast, so The devices producing them just fire them off, and it's up to the receivers to decide if they want to receive those or not. So that's a multicast, a 1-to-n relation. And in regards to the triggering, PDOs can not only be triggered by the application, there can also be various automated triggers, change of state, time, sync, and sync with a counter. The CANopen SDO is a confirmed one-to-one communication method. It can do segmentation when needed, limited to 4 bytes of data when doing an expedited, so a single request and response. And the biggest limitation here is that really the channels available in CANopen are limited. So per default, there's only one SDO client for all nodes. So only one device can be a manager that communicates to all others. With some extra effort there, we can work around this issue, but the default is that it's only one. And last, the CANopen FD Universal SDO brings everything together. It offers one-to-one as one-to-many communication, and the client can also be done by any node. So here truly every CANopen node in the system can issue SDOs or universal SDOs to every other node in the system, allowing to implement a very powerful communication exchange method here.